Oh, we want to say hi to our New York trippers.
Hi.
Hi.
To New York.
Welcome to New York. It's very tall. It is. New York is unique. It's not unique. Probably Chicago is the same way. I haven't been in Chicago in a long time. But New York is fundamentally different from D.C. in that you walk in and it's just very vertical. And the reason for it is space. It's cramped. And it's unlike the other cities that I've lived in and near. So D.C. is not like that. Houston is definitely not like that. Houston is humongous. It's the greater Houston area is larger than Rhode Island.
Oh.
Which is wild. Maybe it should be its own state. So in any event, when I go to New York, I get this profound feeling of just being in this small, really strange, in a mall. Yeah. It's in a strange kind of a space. I would imagine that Tokyo is similar. I've never been to Tokyo.
Actually, not that Tokyo. But like Hong Kong is that.
Hong Kong is like that?
Hong Kong is like you feel like you can't breathe.
You can't breathe. Interesting.
Like it's like so crowded and all the buildings. They're like the space between buildings are really tiny, so like it ends like a stretch.
Can't breathe in Beijing.
Right, that's different.
No, you can go to the Asian subway line 1, line 10.
So,
No, too many people, too crowded.
interesting. Okay, so by the way, I sent a message to you, and you. Did you get that?
Oh, hold on.
Through Edmeadow? I sent a message to you through Edmeadow, so just check. Did you get it? No. Basic communication thing. Check.
No.
Check your lines of communication so you know what's going on. Good.
Oh, I saw it.
Good.
You're welcome.
Oh,
that's your problem. Thank you.
So, are there any questions about the antiderivatives homework that you've done so far?
No.
Okay, good. Just to review, the antiderivative is driven by the mean value theorem, which proves for us that if f prime is 0 on an interval a to b, then f is constant. Right, you say f is equal to c on a to b. And from this immediately proved for us that if f prime is equal to g prime on a to b, then f is equal to g plus c on a to b. In other words, functions with the same derivative have the same function within a constant. So, our derivative rules so far have covered constant multiple rule. What is the constant multiple rule for antiderivatives?
It's integral k f x dx equals k f x.
And there I go. We want to call it antiderivative at this point. But you know that it is an integral. We don't officially know that yet. Sum and difference rule. Let's package those into one. The integral of f plus or minus g is the same as and then we have a whole slew of different integral rules for various functions. Justin, what was the power rule again? plus C, plus the obligatory constant C, and that's our theorem up here, right? Right? But we're missing one other thing.
I am not equal to
Exactly so. And not equal to -1. And then we had a bunch of trig, inverse trig, so on and so forth, antiderivative rules. But we had an important omission, and the important omission, we have really several important omissions. Product rule, we don't have a product parameter rules yet. Chain rule. It should be the case that if I integrate f prime of g of x times g prime of x dx, what should this automatically be?
FGX.
Exactly. Plus C.
Oh, plus.
Now you want to get in the habit of prompting yourself about the plus C. Don't wait for me to prompt you. Yep. Now, there would be a good example of this. If I were so lucky as to have an antiderivative that is set up with f prime of g times g prime, then I could integrate that guy immediately. I could recognize that what I have here is f prime of g, where f of x equals x to the 7th, and, excuse me, f prime of x is equal to x to the 7th, and g of x is equal to 3x plus 4, so that g prime of x is equal to 3, so that this just so happens to be in exactly the form f prime of g times g prime. Hey, it's our lucky day. So I can immediately write the result as f of g of x. And all I have to do is to integrate the form, the outside, and the integral of the outside is 1/8 of x to the 8th, of course, plus c. Coming over here, this would give me 3x plus 4 to the 8 over 8 plus c. And we can check it by taking the derivative. Take the derivative, 8's cancel, 7 times the derivative of the inside, we get 3. There it is. But this is an awkward process, and it's very error-prone, because you can imagine that it's unless you're thinking that way, it's hard to look at this guy and say, oh yes, that's the derivative of the inside, and there it is. Furthermore, it's almost like lightning has to strike in just the right way, because if I change this antiderivative just a little bit, now all of a sudden I can't do it anymore. That's no good. So we need a slightly better way to think about it. And the slightly better way to think about it is going to be substitution. Substitution is going to be the integral version of the chain rule. Actually, it's going to be more than that, because substitution has more than one trick up its sleeve. Chain rule will be the start, but substitution is going to expand and be a powerful tool, a strategy for a broad category of antiderivatives. So let's see how a substitution process can work. The spirit of substitution is that we are going to choose a u. And you, Y-O-U, the problem solver, are at liberty to choose any u that you want. There is no wrong choice of u. Literally, there's no wrong choice of u. However, some u's are better than others. Yes, some u's are the best u's to choose here. Once I have chosen a u, then I need to compute du. And then I need to go through and replace everything in the integral in terms of u. And when I say everything, I mean everything. Integrate. That's the purpose of this whole thing, is to find the antiderivative. Maybe I should use our correct term. Anti-differentiate. And then finally, I'm going to need to back substitute. And this process of substitution, I call it the spirit of substitution, because the spirit of substitution is you can pick any u that you want. And so that gives you a lot of freedom. This process is going to be the process that you're going to walk through in every single homework problem, blah, blah, blah. All right, so let's see how this works with one of our antiderivatives. And we'll start here with this guy. The first thing that we observe about our antiderivative is that it looks like a power rule. The form is power rule. But I have an inside function. And so the most common strategy for substitution is to let u be the inside function.
Yes.
Strategy tip. U equals the inside function. So we begin by choosing u equals the inside function. And immediately we compute du. And du is a legitimate differential. It's going to be equal to u prime times dx. All of this is very straightforward. Now comes the process that students sometimes find confusing, but by the end of the year last year, you probably were good at. And that is we have to come back through and replace everything in terms of u. That means that the 3x plus 4 must go.
Usually this happens.
And the dx must go.
3 times the 1/3 du.
Yes. And you got that 1/3 du by solving this equation over here, the differential for dx. Yep. And now that I have that, with the aid of a little bit of constant multiple rule and a little help from my friends, I can find the antiderivative in terms of u. What do I get?
21 or 24 times the base. Plus 8. And there is because of u.
That's right. We now need to back substitute because this answer, while correct, is in terms of a variable that I made up. And because I made it up, it is therefore not an appropriate answer for the original question, which knows nothing of u's. So I need to back substitute and replace that u, or in the words of Monsters, Inc., put that u back where it came from, more so called. Now, substitution is a great process, but because the process itself involves many different activities, it's entirely possible for us to mess it up. So we want to check ourselves by taking the derivative, and we're going to check how often? Always. Yep, we're going to check it always. So we do a quick check. And we check. You can do most of the differentiation in your head at this point. We get 1/24 of 8, 3x plus 4 to the 7th times the derivative of the inside. We observe with great satisfaction that we do cancels, and we get exactly the original integrand back. I used that word integrand, by the way. The integrand is the thing that we are integrating. Somehow I can't help myself. I keep on calling it integrals. So that's our process. It turns out to be a really powerful process. And at this point, I'd like to share with you some different integral situations that we can use this for. Now, there we go. This antiderivative shows up in the computation of probabilities, both in terms of statistical analysis and also in quantum mechanics. And so it's a nifty function, and we'd like to find its antiderivative. And so we observe that we have a product of two things. And because we have a product of two things, that suggests to us that maybe we're looking at an outside-inside situation, a chain rule situation, and that's a substitution. So let's consider what we might wish to pick. Any candidates? Negative x. Why negative x? I used to guess. Well, instead of taking a guess, remember our strategy tip.
E to the negative x.
Remember our strategy tip.
We find the root.
Bing, 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 bing. Inside function. Negative x squared. Oh. Will that always work? Not necessarily, but it's a great place to start. We're going to try u equals negative x squared because it is an inside function. Now walk through the rest of the process for me. Who's got this? And what was that equal to again?
Then we can replace that to 1/2.
Is equal to?
X.
Yeah. There's x.
There it is. Yep.
But there is the e to the u
Uh-huh.
equals times negative half the u.
Good.
1 plus 1.
No.
Oh, never mind.
No.
Hold on. E to the u.
E to the u. Sure.
And then the e to the u.
Wait a second.
Oh,
You're falling apart on me.
Over the times 1 over u.
Do you now?
Hold on.
What is the derivative of e to the x?
E to the x times dx.
No, what is the derivative of e to the x, not the differential?
E to the x.
It's e to the x. So what is the antiderivative of e to the x?
E to the x plus
Interesting. All right, so let's come back here. What is this antiderivative?
a negative.
Let's see. Thank you. Hell yeah, it has common with the fact that you're supposed to remember your plus C's. Good job. All right. And where from here? Go ahead.
E
Yeah.
to
E
that
to
case.
the X.
Okay.
Thank you. Go ahead.
So, negative 1/2 times negative
Outside inside.
oh, okay. Yeah, negative 1/2 times e to the negative x squared times negative 2x.
Uh-huh. Uh-huh. And we have exact match. So good. Now I want you to notice something that's really fascinating and interesting. Let me have your attention on this. The thing that's fascinating and interesting is you guys are good calculus students. You really are. But when I throw you into the pool and say, here, integrate this thing, all of a sudden you start stumbling all over yourselves about integrating e to the u. You're normal. The reason this happens is that you are trying to juggle a lot of different factors all at once, a lot of different ideas and concepts and skills all at once. The process of substitution does that to you, and it is good for you because of that. But you absolutely positively need practicing. So if you're thinking about skipping tonight's homework, where do you think you're like? You don't want to skip this one. Because, in fact, for the integration techniques that we're doing, you don't want to skip them because there's so much detail, so many different things that you have to get right, that you really have to practice getting those things right, or you're going to flake. All right? So, good. On we go. Go. I'll pause this. If you are playing along at home, you can pause the video at this time and do this integration yourself. So, the u you chose was? And keep going. You're on.
So, du equals 5dx. So dx equals 1/5 du of du. So, let's integral secant squared u over pi. So it's a tangent u times 1/5. So both things over 5 times secant squared I x times
We're good.
Oh, I missed the chat.
Did you miss the check?
Yeah, you said I missed.
All right. Now, let's go into some really interesting situations. Whoa. Remember this? Yeah.
Linear.
This one does not have an inside function that's obvious. We could try to use the denominator. So if we try to use the denominator, see if it's going to work. Then we compute the du, and and we get x times 1 over x plus ln x dx, which is 1 plus ln x dx. And just looking at my form right here, it is not at all obvious that I've got a 1 plus ln x anywhere in the cards. So, the moral of our story is this. This is the first time we've encountered this, but it's going to happen. You choose a u, and you evaluate the choice of u by first computing du, and taking a look and seeing if you can find du. If you cannot, then don't cross this out utterly, but put it in your back pocket. You take this guy and we're going to put it away, because this looks like it's probably not a good choice of u. Now, the reason I don't want you to dismiss it entirely is that when we run out of u's, sometimes we come back and we say, let me rethink this, and maybe we can find a way to make this u work after. Okay? So, but before we do that, we're going to consider other possibilities for u. Any ideas? Let's try letting u equal natural log of x. That is a particle or fragment in my denominator right here, and it might be a good choice. And we're going to evaluate that choice by computing du. What is du?
1 over x. Oh, dx.
Aha! Look at that. Du is sitting right there in front of us. It's mathemagical. So that when I replace, I get du over u. And du over u is a very, very friendly form for us. This is the log form. We're going to actively seek out the log form when we can, because it is extremely useful. But natural log of u has to be back substituted, so that I get this really interesting function, which does actually show up in analysis, the log of x. In computer science, algorithms that run in log n time are very, very fast algorithms. We love log n processes. Okay? Mhm.
I remember this.
I remember.
Good. Let's consider two integrals that look similar but are different. What's this guy?
Inverse.
Inverse tangent.
Inverse tangent.
Okay. Let's see.
How about this?
This one.
And we can take. Isn't like inside all of them equals?
Okay. So what you might we suggest? First of all, we ran through the catalog of functions first. First, we looked for an instantaneous antiderivative. We didn't find one. Here, we had an instantaneous antiderivative. Here, we look for one. We don't find one. So we think substitution as our next line of defense. And when we do, what would you suggest is our u?
Okay, I was considering inside because we have the policies.
Right, there is no inside. So try it.
X.
One plus x. Yeah, I'm trying.
Equals X.
And du equals 2x.
Mhm. And how does that look compared to what we have?
Yeah.
Yes.
Then 1 over du equals, like 1/2 du equals x dx.
Which we have. That's exactly right. And Justin, I prefer to think in terms of substitution rather than canceling if possible. So that now my integral transforms as what?
U 1/2 U
You sure?
plus
Does this U match my form here?
D over
Yeah. Yeah. You gotta be careful about numerators and denominators, right? Keep going.
plus, no, match 1/2 natural log. Absolute value of U plus
Yeah, let's see.
equaling 1/2 natural log. I think we don't really need the absolute value.
Good point.
1 plus x squared.
You make an excellent point there. Why don't I need the absolute value?
It's positive.
Yes, our argument, there we go, is always positive.
Check. One half natural log of 1 plus x
Is what?
is 1/2 1 over 1 plus x squared 2x. That's it. And pays off to. Excellent.
Good. That's good.
Like, if you screw up to last one, like, how is it? And for this one, like, do we need to set U not equal to 0, or
That's a great question. That's a really, really good question. What about the domain? Let me take a minute to actually write this out. When we consider the domain of the integrand, because the integrand contains this ln x, the domain of the integrand is going to be x greater than 2.
Do we need to consider this when we're solving this problem?
Yes, we do. We do need to consider it. It's going to become important when we do the differential equation stuff. Because what we're going to say for the solution of our differential equation is that the solution of the differential equation must be continuous and differentiable on its domain. So that may mean that we have to make a branch choice. It may be that the function that we get as our solution has a larger domain than the problem allows. And we'll have to artificially restrict that domain in order to accommodate the right branch. So when I take a look then, interestingly, at my results right here,
It's hidden.
yes, what I see is that the natural log of x has got to be a positive number in order for this to work. And because the natural log of x has to be a positive number, therefore, that means that x has to actually be greater than 1. So what happened? How did we end up with stuff? Well, it's because I was a little sloppy about identifying the domain of the integrand. Let's come back here. ln x will be 0 when x is equal to 1. Yeah. But also over here I was a little bit sloppy because I did not consider the absolute value signs. As it turns out, I just want x to not be equal to 0. Excuse me, I want natural log of x to not be equal to 0. And therefore, I require that x not be equal to 1, but as it turns out, the integrand has that property already. That 0 to 1 is also part of the domain here. So it turns out we're okay for this, that the integrand domain is consistent with the antiderivatives domain. But this one was an interesting, tricky thing. Okay, I want to consider now, we did two similar looking antiderivatives that had really different results here. And I want to consider now, yeah, we have time for this. Let's do this. Let's make it 16 so this doesn't look like an A or something. Okay. These antiderivatives here are what I call inverse trig forms. And you can see why. These are the inverse trig forms because they're in the form of something that looks like the derivative of arctangent. Could also be arcsine, could also be arcsecant. Let me get these inverse trig forms down for you so that you'll recognize them when you see them. So we have our 1, 2, 3 inverse trig forms, and I recommend making a note of them because we're going to see them. We're going to handle them in two layers. Today, I'm going to handle them by just offering up a possible substitution that makes our lives easy. In the future, we're going to handle them by actually doing a trigonometric substitution. But that's not going to come for some time yet. Okay, everybody got the forms down? The inverse trig forms? Now, for these inverse trig forms, there is an indicated substitution that will work very well for you. And that is that we're going to let u equal x over a. And the reason this indicated substitution is going to work really well is that it's going to allow us to get a common factor of a squared here that I can then factor out for the whole thing. Let's see how this works in this process. If I let u equal x over 4, then du is equal to dx over 4. Or in other words, dx is equal to 4. Now I'm going to come back over here and I'm going to back substitute. And notice that I have two things to substitute. I'm going to substitute, excuse me. And you notice that I've got two things to substitute. And one of those is the phrase 16 plus x squared. So I need to replace x with something.
4u squared.
Exactly. X is for u. And when you substitute, don't forget your parentheses. Dx is equal to 4du. Well, this is delightful because now in the bottom, what I get is 16 plus 16u squared. And I can factor out my common factor of 4 and my common factor of 16. And what I'm left with now is an exact antiderivative of inverse tangent. But we need to back substitute. When we back substitute, u is equal to x over 4, and there you go. Well, I need to check it. And the check actually requires a little bit of cleverness. Course constant multiple rule. 1 over times the derivative of the inside. The problem is that when I look at this, this does not look like my original integrand. Or does it? Let's simplify. 1/4 times 1/4 is 1/16. Oh, would you look at that? So that when I multiply through, it's mathematical. Yay! It all works out. And this will occur the same way every time. I don't remember if I put one of these on tonight's homework. I know there's one on tomorrow's homework. This is kind of new. We did it last year, but I just sort of waited. We're going to do a lot more of this year. You're going to get very, very good at integrating. That's one of my learning goals for this class, is that you guys become experts in integration. And you'll actually like the results, because what happens, as I mentioned, is that you have to take all these details and coordinate them, so you kind of feel like your brain is on. You know? And so it's very satisfying process.